system operation plus basic set point configuration and IO status overview. But on the right hand side, when we see the intelimain's base box or intelimain's NTC base box, there are two versions. One is NT, where you do not have enhanced communication port like a USB or a secondary RS485 or a Ethernet port. And there is NTC type, which would come with USB, Ethernet, and a secondary RS485. So this is a DIN rail mount module, and you will need an HMI, which will be again ComAp HMI from a 5-inch, 8-inch, or a 12-inch HMI, which you can attach to this base box controller. The intelimain's controller does not influence or does not directly control the genset. So basically, if you put an intelimain's controller to monitor the grid side control, so it can open and close the mains MCB, but it will not physically directly control the generator to kind of like start, stop, or breaker close and open, and nothing of that. So it is just taking care of your grid side control. There is no direct influence to the genset, but indirectly it can perform load sharing, var sharing, and other factors of control, which we'll be addressing in today's presentation. And let me know if you feel my voice is too loud or too low. I can adjust accordingly, because there was some request during the last seminar that it was not that audible. So please do let us know. Okay. Now, how does it then influence or control the genset control part? The intelimain's controller would talk to the genset controllers over the CAN bus line. So we have a secondary CAN2 bus, which is our proprietary CAN bus communication line, where it can exchange information or send information from the intelimain's controller to intelligent base box controllers. It can send start-stop signal over the CAN bus, so you do not need to have a physical wiring between the grid failure trip signal to the genset controllers. You can share that information over CAN bus using the share binary output modules. And what all other features it gives you? It definitely gives you load sharing capability. That means if you want to run parallel with a utility system or grid system, so you can basically perform CAN2 bus communication and perform load sharing and var sharing. You can also have island operation. So once you have grid failure, the gensets would operate in island mode, and the intelimain does not play any operation or control when the system is operating in island mode. Synchronization of group of genset, that means we can definitely synchronize a group of genset to utility system if and when required. Most of you might be kind of familiar with a single genset parallel to grid. That is a single controller doing simple paralleling or peak saving or standby application or close transition solution using a SPTM application. Here with intelimains, we can cluster a group of genset to reverse synchronize with the utility system or run in parallel either in base load or import or export control. Yeah, again, as I already highlighted, we can do active and reactive power sharing as well. The key 4 features when we talk about load sharing and var sharing, when we want to do paralleling with utility system, is to the setting. So if you look into the setting of intelimain's controller, which I'll show you later on again in the software, we have primarily 4 or 5 operations. One is base load operation, which is what you see here. Let me just bring the pointer. So you can see under the ML load control. Hold on. Yeah. Once we have ML load control PTM, you have option of system base load operation, or you can have external base load control. So either you can give a fixed base load by set point by fixing in, say, 1 megawatt would be the base load, or you can have a variable base load by a potentiometer or certain kind of like an analog signal. You can configure a base load using that, or you can operate in import or export control. So if you want to do grid paralleling and only supply back to the grid or only take a certain amount from the grid, you can set. And the 4th option is external import and export. So you do not want to have a fixed value set through the controller, but you want it to be dynamically changed by an operator from the panel. So you can have external import and export. And last one is by temperature by power. So depending upon your alternator winding temperatures and all those parameters which you are observing, you can influence your power capacity on the gensets or even on the transformer end by reducing the kilowatt if the temperature shoots up. That's how we do it. Now we'll try to address one by one all of these, the system based load or import export control or by power. So it's pretty straightforward, as I was trying to show you, that we have these all 5 options available for you, and depending upon your operations requirement, you can configure this one of these into the set point to allow the controller to behave in a certain manner. And based upon your choice of selection, it will either behave in load sharing, var sharing mode, or it can work in base load, base power factor accordingly. And it will influence the genset controllers to behave in a typical manner. Okay, so when we put it into load sharing mode, for example, you want to perform no base load but standard load dependent start stop or load based power sharing between the genset, you can keep it on the load sharing on the intelimain's controller, and also on the genset side it automatically gets influenced because all of these values are shared over the CAN bus, and the controller would basically adapt to the load on the bus and switch on and switch off additional gensets if and when required. But when we choose, say, suppose example, base load operation. So this is a typical example. Say suppose you set a base load of 300 kilowatt on your system on the intelimain's controller. So this is your system's base load, and you have 3 gensets on the bus and one intelimain's controller on the grid side, and each of your genset is rated to 100 kilowatt, 200 kilowatt, and 300 kilowatt. So now because of the base load request of 300 kilowatt, based upon their nominal capacity, the gensets will subdivide this load between them in ranges of 50 kilowatt, 100 kilowatt, and 150 kilowatt to meet up the total base load requirement. Then as we move forward, active power regulation in parallel, when we talk about different examples of base load, say suppose the 50 kilowatt, I set a base load of 300 kilowatt and I enable the export limit. So I want to export additional power, basically is enabled, and I want to just take 50 kilowatt from the utility and rest has to be supplied by my generators. So here we have, so the base load is 400 kilowatt. So if you see 100, 200 and 300 kilowatt genset, each of them will take 50, 100 and 150. So I'm meeting the 300 kilowatt, and the mains import here is 100 kilowatt. As we move forward, the next example is again based upon different sizing of genset. So 300 kilowatt of base load. So I'm sharing 42 to 83 and 125 kilowatt. So total is 250, and the mains import again here is 50 kilowatt. So the total sum will always be based upon how much you are importing or exporting and how much base load operation you want to achieve between them. This will be more clear when I will show you with examples of illustrations later on. Then we have actional base load control. Say for example, your customer or your system operator wants to have no influence through the controller's HMI or through the set point to keep changing the base load, but rather he wants to have a potentiometer which would allow it to change the base load on a daily basis. Instead of having a fixed base load set point, he wants to configure or basically modify it on regular day-to-day operation basis. So we can again do that by bringing in actional base load control. So we can go to the set point and we can configure an analog input like a standard potentiometer. Maybe you can use a 1K pot or 2K pot. That potentiometer can be mapped to the base load of, say, suppose 0 to 100% of whatever range you want to operate. And that can be connected to an external base load control in the function list, which I can quickly show you. How does it look like? Just hold on. So if I go back to the genconfig archive here, so this is one intelimain's archive for your reference. So this is where we can set up our base load operation. So whether it is system base load, whether it is external base load, import or export control, or external import export control, and last one is temperature by power. So if you're not clear about any of these set points, just press function F1 or press F1. There will be a help window opening up on the ComAp, and it explains you all of these functions which are listed, the 5 functions, and how does they influence the operation in real time. Now, if I choose my system base load to be external, that means I want to configure the base load by using a potentiometer and not by having a fixed base load of 1000 kilowatt. Once I have set it here, external, I can go to IO, analog input, and I can choose one of these analog input, and I can create a function. If not, I can even make my own user sensor curve, first of all, depending upon the type of potentiometer I'm using. If it is a resistive potentiometer and I name it base load, I can set the resolution accordingly. So you can choose, and I can have say 0 to 100% and 0 to, or maybe this is resistive. So if it is, say suppose 2 kilo ohm maximum is the potentiometer range. So here we can go up to say 0 to 1000 kilowatt is my sensor curve ready. I go back to my IO. I choose this, and I can choose my sensor. So my sensor is, if you scroll down, you will find something called as base load, the one which we prepared. And we have set it as, I can make it kilowatt. Yeah, so dimension is set to kilowatt. When it comes to function, I can look for, you can see here, external base load control, the function. And if you are not sure of that function, again, you have the choice to click function F1. This input is used for external determination of system base load. So once you have done that, and once you rotate that potentiometer now, that potentiometer would vary from 0 to 2000 ohm. And at say suppose 1000 ohm, it will give you near about 500 kilowatt of base load. So you can vary this value. So just by selecting your set point and choosing the kind of operation you want, whether you want to have a set point based base load or you want to have external base load control. So this is how the base load operation works. Or if you decide to have import or export control, so again, you can set different import value here or export value here accordingly, and how much of importing you are allowing, or negative is export. Or if you decide to put external import and export control, so the same behaves in this manner. We can make another sensor curve for import and export control, and the choice of function here will be this external import and export control, the second function. And this will be the externally controlled system import and export between the utility system and your group of genset. So it's pretty straightforward, just few set points which you need to worry about, and that's how you control. Once we go back to the presentation here, so you can choose whether you want to import or export, or if you just want to operate on base load operation here. As we move forward, an example again. So for example, in this case, I have import of load of 100 kilowatt and my system base load is 500 kilowatt. So with the 3 group of gensets, I am loading at different capacity, 67, 133 and 200 kilowatt. So the total sum becomes 400 kilowatt and the mains import remains 100 kilowatt. So my total load, system load, is somehow met with that. If I have a system load of 800 kilowatt, I'm taking 600 kilowatt, the full capacity from the genset, and whatever rest is required comes from the utility system. So this is how your import export or your base load operation works. Now coming back to the application perspective, like there can be different applications which you can use with intelimain's controller. So we categorize the intelimains to work in four different variations. The hardware still remains the same. You just have to choose the application archive, which can be uploaded into the controller, and it would perform the specific function based upon your application archive. So the first one is your MCB application, which we call it mains circuit breaker application. The second one is MGCB, which is your master generator circuit breaker application. The third one is your bus tiebreaker application, where you can perform bus coupling between different group of genset. And the last one is your feeder application when it comes to feeder control or load control on the system. Now, what exactly happens on the intelimain side? We have already covered the three-phase current sensing and voltage sensing is available, and you can perform this base load operation. Now let's look into the example perspective. Let's address the first one, for example, MCB application. This can be a simple example or illustration of a site where you have two gensets on the common bus, and you have your utility system coming in. So when your utility is healthy, this circuit breaker or switch gear is closed and it feeds the load at all times. Your backup generators with your IntelliGen base box are available here with application as Mint application. And on the IntelliMains controller, since you have only one switch gear to control, you are using MCB application here. So as you can see here, it can close and open this breaker, plus it takes a feedback. It has a three-phase bus voltage measurement and three-phase grid voltage measurement plus current measurement. And your genset controllers are independently taking care of individual genset control and protection, but they talk to each other over the CAN bus. So upon grid failure, the controller would send a signal over the CAN bus to start the genset, synchronize if required, and start feeding up the load. And once the grid returns, we can reverse synchronize and do a soft load transfer. So what are the functions which we can specifically address? So we can do MCB control. Then again, your protection and isolation is performed by the MCB side. Then we can have automatic genset start and break transfer upon failure. So once there is utility failure, the genset kicks in and takes care of the load. We can even perform MCB synchronization upon return of utility. So once the grid is restored back to normal, we can reverse synchronize and perform load sharing for a short term and do a soft load transfer, or we can work in import export control if required. We can do power management. So standard power management functionality between the genset still remains the same, load dependent start stop. Load sharing and var sharing is possible. Soft loading, unloading of genset. So we do not do a bump transfer, rather we do a smooth transition. Again, you have reverse power protection on your utility side. You can have vector shift and row code protection, and other voltage unbalance, current unbalance. All those protections are inbuilt. The only protection which we do not cater currently is differential protection on our control modules. And you have base load operation. Now let's look into the simulation. So for a simple MCB application, you need one IntelliMains controller and couple of genset controllers. How exactly does it look like in reality? So for example, if you see here, I have currently my utility system is healthy and no problem at all. So my MCB breaker is controlled by the IntelliMains controller, and it measures the utility side voltage and current. It measures the bus voltage. So once the utility is healthy and secure, so it closes the MCB and continue to feed the load from the IntelliMains controller. My genset controllers are on standby and they talk to each other over the CAN bus. So upon utility failure, so suppose there is a grid shutdown or something happens on the grid, the controller does not see any more grid voltage. The moment it doesn't see the grid voltage, so there is a valid timer. You can set up the timing and automatically it will open up the MCB. Once the MCB opens up, the IntelliMains controller will send this information to the genset controller over the CAN bus, or you can even have hardwired signal. So the both of them is fine, but we can again save cost by sharing the information over the CAN bus, and the genset controller would start, close the breaker and start feeding up the load. As the load increases, we can perform standard power management. So load dependent start stop comes into play. And they synchronize and they feed the load if the load goes up. And once the load falls back, automatically it goes back to one genset. But after a while, when so say the genset has been feeding the load for quite few hours, and once the utility system is restored, so as you can see, the genset controllers do not see what is the current grid voltage and grid frequency, but the intelimain's controller does see that. It is constantly monitoring what is the current voltage and frequency. So based upon the current voltage and frequency being measured on the utility bus, it sends the signal over the CAN bus to the genset controllers to generate the same voltage and frequency by regulating the speed governor and AVR, or ECU and AVR on both of these gensets, and try to match the voltage and frequency amplitude same as the utility bus. So once the parameters are matching and the phase angles are in close proximity, we basically perform a close transition. So we close the MCB and all of the breakers are closed. So we transfer the load from the genset bus to the utility. So we do a soft load transfer. Once the load is transferred to the utility, the genset breakers will start opening up and the gensets go back on standby. So basically we just had one power cut. So upon grid return, we can do bumpless transfer, or basically without interrupting the load for a short while, we can transfer in a closed transition mode. But if suppose there is a regulation from the local utility company which tells you that you cannot perform paralleling operations, say for example in Singapore, so you can definitely put up a set point on the controller. We have that option to have break before make. So that means you can open up the GCBs and perform MCB closing. So there will be two power cuts. So that operation can also be done like a standard ATS operation. But if you want to do close transition, it's pretty smooth and without any interruption, we can perform that. Then there can be another example, simple MCB application, and what could be its limitation. At times, this is very common across APAC or Asia Pacific, I would say. The load or the gensets when initially sized up or initially put into a powerhouse are not anticipated for future load increase or future load growth. Say for example, over the period of time, my load increased from say 500 kilowatt to 800 kilowatt, but I haven't upsized my gensets. For example, in this scenario, where I have just two gensets of 500 kilowatt each and my total load on the utility is 800 kilowatt. So every time I have to perform load shedding before I start my gensets. So in this case, when I do not do that, and if my utility is okay, I'm feeding a 800 kilowatt of load. Now, if the utility fails or if the grid fails, the MCB open up and basically I will start my generators. But my genset is undersized and basically it will get overload and it will trip. The second genset would try to attempt and to take the load. But again, the same happens because it is as well undersized and it will trip. Until unless I reduce the load or terminate certain feeders, I cannot feed the load by using my undersized genset. And this is pretty common, and at times there are operators just to trip certain amount of load up after the grid failure happens so that my current genset capacity can take care of the load. Now, until unless the grid returns, I cannot feed the total load on the system. So once the grid returns, it goes back to normal. To overcome this, either we need to upsize the gensets or we can look for another solution, which we call it MGCB application, Master Generator Circuit Breaker application. Here, we do not need to add any more controllers here. The same controller which was acting as MCB before can be upgraded or just reprogrammed with a new application archive, which is called as MGCB application. So now, instead of controlling just one circuit breaker, which was MCB in the previous example, now you can control two switchgear on the bus, which is your MCB and your master circuit breaker. So controller still remains the same. The genset controllers are as it is. We can talk to each other. The only isolation which we did here, or only addition point which we did here, was isolating an additional switchgear, which is MGCB. Overall functionality still remains the same as similar to the MCB application. it's just an extra MGCB synchronization option you have. I can explain it in more simple illustration example. So as you can see here in this bus, I have two gensets and one intelimain controller taking care of MCB breaker and MGCB breaker here. How does it look like in example wise? Say for example, if my grid is healthy and it is feeding up the load without any trouble, and once the grid fails, the intelimain controller will open up the MCB after there is no voltage being sensed on the utility bus. It will send signal over the CAN bus to start my genset. So the first genset starts, creates a bus voltage. So there is, say suppose LV or MV, doesn't matter, we have, or even HV, we created a bus reference voltage. The second genset would be started. So the second genset will try to synchronize with the first genset, and they are performing load sharing and var sharing between them. So everything is normal. Now automatically once both of these breakers are closed and this information is relayed back over the CAN bus to the intelimain controller, it acknowledges both gensets being running and both the circuit breakers being closed. So I have enough reserve. So I'm good to close the master generator circuit breaker. So I'll close the MGCB and I'm good to feed the load. So I just isolated this common bus with an switchgear here. And upon grid return or upon grid getting stabilized again, it constantly monitors the grid voltage and frequency. Then it sends the signal over the CAN bus to regulate the AVR and the speed governor or ECU on both of these engines to match the voltage, frequency and phase that of the grid voltage, frequency and phase. And once everything is matching, we perform a closed transition. We can transfer the load back to the grid, do a soft load transfer, and the gensets can go back on standby. That's pretty simple approach with MGCB application. The controller still remains the same. You do not have to procure additional control module for that. We can even perform again load reserve start stop, for example here. So if you're having a requirement like peak load or peak saving functions and stuff, we can perform that as well. Now looking into the third application, which is another interesting requirement, where we have basically a common bus or common coupler. So you have powerhouse one with, say suppose one or two or more gensets on two group. There are multiple utility, and in between I might consider having a bus coupler if and when required. Let's look into that. Say for example, I can have dual bus, dual utility, and then I can have individual genset banks at both ends. And this bus tie breaker is good to synchronize between the common bus, between the genset. It does not perform synchronization between utility. So if suppose one utility is down, so it will basically open up the MCB and it will close the BTB here and feed the power from the second utility to the load on the left hand side or right hand side accordingly. So how does this happen? So we have something called as control group or group linking into the controller. So this group linking methodology allows us to cluster a group of gensets or group of system on left and right bank to combine and work as a common group here. Say for example, the group on the left, which has 3 generators, I can name it as group 20, and group on the right with 1 generator and 1 utility system, I can link it as say group 11, so left and right. So on the BTB controller, I can put group link left as 20 and group link right as 11, and once basically this bus tie breaker closes, so this becomes a common group. A more simple example or basically a more diverse example of explanation could be here. So as you can see, there are 2 utility systems. So this is my control group 1. So this top group is a single group individually. It can be 1 genset or group of genset here. So they are individually operating between them. And this is the second group of genset and grid system, which is operating on the bottom half. So let me just bring the pointer again. So this half on the top is 1 cluster, and this is on the second cluster. So in between there is a bus tie which is gonna combine these two individual groups to work in a common group. So once the breaker is closed, or once the breaker is kind of like closed and the feedback is there, it can combine these two groups to work as a common group. So as you can see here, we cannot do grouping between utilities because I do not influence the voltage and frequencies between the utility, two different substations. So this is not possible, but rather the second one is possible, where you have influence between the two genset groups or two uh, buses, where I can influence the voltage and frequency to match. On the top end, I can just transit from one utility system to the other utility system. So for for a simple question here for everyone, if you see this schematic or single line drawing, where you can see there are three incoming utility system, and I have three clusters of genset groups, basically four clusters of genset group. And if I want to combine them into logical groups or cluster them together at one point of time, I want them to work together. So how many groupings which you can think of in your head? Like, how do you see that? So let me kind of explain it to you here. So the first group which you see is one utility and two gensets can work together. So basically, if the bus tiebreaker 1 is open, if the grid fails, the gensets will start feeding up the load. If the grid is back, the G1 and G2 can synchronize back to the grid and they can work independently. Then the second grouping is this individual genset. So suppose if you close GCB3 and if you start GCB generator 3, that can go to the common bus here, and it can also feed a load on this common bus upon this bus tiebreaker control. Or if there is a load here on this bus, it can feed the load individually. So this is the second group of genset. Then the third group of genset is or third group of cluster is this, where I have utility 2 or the grid 2 with genset number 4 and 5. So they can work independently on its own. And the last grouping here is basically your individual MCB here, because there is a bus tie involved here. So this is your third group and this is your fourth group. So now if you close all the bus ties, BTB1, BTB2, BTB3 and BTB4, it will become a common group. So the group linking or group link left and right is what you have to key in inside the bus tiebreaker controller set point. So if your left is 1, your right will be 2. If your left is 1, again right will be 3. If your left is 3, the right will be 4. So you can cluster them and allow them to link and operate in different sequences. So that is very straightforward here to cluster them in different forms. This is another example of a H system which you saw. So suppose there are multiple utility coming in, so you can have intelimain's controller to take care of individual MCB. Or if you want further isolation to operate as an individual bus tiebreaker controller, you can put in that here, another BTB here, another MCB here, and another BTB here. But you can also consider just one intelimains to control it as MCB and MGCB operation. But if suppose this is high voltage system and you want to have a step up transformer and you want to further isolate the system for maintenance purposes, we can use a bus tiebreaker application to isolate your generator bus to the common bus. Example wise, how does it look like? Say for this example, which you can see here is, let me remove. I have two utilities. So the grid 1 and grid 2 feeding up my load without any problem. And I have two generator groups with a single generator 500 and 500 kilowatt. And in between, I have a common bus with a bus tiebreaker controller. So if my utility fails, my MCB1 will open up. So instead of starting the genset, I could just close MGCB2, BTB, and MGCB1, and I can feed the load from the second substation to the top side. This is pretty common in these days in data centers or hospitals, which usually take a dual substation feed into their system, and they can switch to substation 1 or substation 2 if under any scenario one of the substation fails to supply the power. So it's pretty straightforward, and we can just couple the buses by using a bus tie breaker, and we can start feeding from the substation 2 to both the buses, which is your, say suppose, IT load and a building load or compressor loads, or if it is a hospital, the critical system and non-critical systems can be combined. So, and if the load further increases and you do not want to take enough power from the utility, you can even perform say standard base load operation or import export operation, and you can load share between the utility system. Once my other utility runs, I can synchronize and go back on standby. This was under one utility failure. But the second scenario, where if both the utility system fails, or when you do an annual shutdown kind of a sequence to kind of emulate overall system behavior, what happens when the complete substation failure happens. So suppose if I create a grid failure on substation 1 and substation 2, both of my MCBs, MCB1 and MCB2 will open up. I'll start the genset, close the GCB, close a bus tie breaker, combine, and basically synchronize my second bus to the first bus. This is not required, but you can also do it. Say suppose on the group 1, where you have just generator 1, maybe there are 2 or 3 generators, maybe 1 or 2 are under maintenance, and you do not have enough reserve from the top half to take care of the load here. So that's why you want to combine this powerhouse, first powerhouse to the second powerhouse, and support the load on the top half and the bottom half of the system. So I can basically combine these two group and parallel the clusters, so group 1 and group 2, by using a bus tie breaker. It creates a common path or common bus, and once they are available, I can start feeding up the load. So the load is active. And once my utility returns, so basically I will perform a short-term paralleling with the top utility first, transfer all the load, do a soft load transfer, and now the grid is taking care of the load. Similarly, when my bottom utility is back, I can synchronize it individually, transfer all the load from the genset bus to the utility, and then gradually put the system on standby. So that's standard operation. The last application is basically the feeder application. The feeder application again allows you to have priority based feeder switching or load optimization, like when we do genset optimization by different size and kind of like ratings, and also how old and how new gensets are, we can sequence them and different priority based operation, like my new gensets are always priority 1, the older ones are priority 2 or priority 3, the least priority accordingly. But similarly, when you have a big infrastructure project, or if you have different outgoing feeders, and the customer wants to subclass your outgoing feeders into priority and non-priority, we can cluster them here by using our feeder controllers, which can, based upon the communication with the genset controllers, it can see how many genset are available on a given point of time, how much is the current active reserve, and based upon that it will automatically isolate the non-priority feeders and keep feeding the priority ones. So that's pretty straightforward application here as well, and you can also load shed at different levels with using the feeder controllers. So that's the fourth example of intelimain's controller. So overall, that's the application perspective. The software still remains the same. We are using IntelliMonitor for monitoring purposes, and we are using the GenConfig software tool, which I just showed you earlier, with the set point and IO configuration and basic configuration on the controller, where you can use it for programming and modifications. The controller operates in basically 4 modes. One is off mode, where basically you're isolating the system from the bus. That means you can do maintenance or you can do any troubleshooting. That means the controller does not have any control on the switchgear, or any functions will happen in off mode. The second one is manual mode, where it is supervisor dependent or operator dependent, from the controller screen or from the HMI. You can open and close breakers. You can perform synchronization. The system will not start upon grid failure. It is waiting for the operator to give it operation commands. So everything is manually operated. Once you switch to auto mode, and based upon your current configuration of MCB or MGCB operation, the system automatically takes care of the load switching between the utility and grid accordingly, and it will perform load sharing, var sharing, power management, and other functionalities. Um, and the last one is test mode. So the test mode is again basically for factory testing and emulating of grid failure to see if the genset starts, synchronizes and takes care of the load, and once you test on load mode function is deactivated, it goes back to your MCB operation. I have some sample schematics for you before I could show you a quick demo on a simulator kit. There could be various examples of system interface. This is very typical, another example where you can have multiple utility, multiple genset, but no bus tiebreaker operation here. So you have individual genset controller taking care of your genset control and protection. So it is measuring the three-phase generator current and voltage, and it is measuring the common bus voltage. It takes care of the AVR and speed governor control of individual genset. Same goes for the second genset. And on your intelimain's MCB application, you are controlling the MCB1 and MCB2. You're taking the feedback, you're monitoring grid side current and voltage, and you're measuring the common bus voltage, which is created by the genset bus. And they talk to each other over the CAN bus or secondary CAN2 bus to share information. That's one typical example, which you already saw earlier in my explanation. The second one is multiple utility system, multiple genset group, and in between there is a bus tie. So this bus tie breaker cannot synchronize the utility system, but this can synchronize your genset 1 with genset 2, because it is again sharing information over the CAN bus, and it is also measuring the bus left voltage and bus right voltage. And once the voltages and frequencies are not matching, it can send request to the genset on the left bus or the right bank to regulate the voltage frequency. And once the phase is close proximity, it can close the bus tiebreaker. So it has a sync check protection and other voltage and balance and current and balance on the bus. There can be examples where we can combine MCB and MGCB application, but again with individual controllers where you have high voltage system and you are putting up a transformer in here and you want to isolate this transformer outgoing with the common bus. So you can put a bus tie breaker here. So we can further cluster them into 3 bus tie breakers. So there is another illustration for that, but overall principle of operation still remains the same. You can go for multiple utility again, so we can further subcluster them. So 3 utility system on the left hand bank, and there are 3 clusters of gensets on the right bank, and in between you can think of multiple bus tie to isolate individual groups. So this is the top half is one group. This is your second group in between with MCB2 and genset 2, and the last one is MCB3 and genset 3. So this is 3 groups, and in between these bus tie breakers allow you to cluster, say, genset 2 to genset 3 or genset 2 to genset 1, or even if you can close all the bus ties, so G1, G2, G3 can synchronize between them as well. This is the same, but the number of genset on each cluster we can increase. So as you know, the magic number is 32 controllers, which can synchronize on the CAN bus. But if you have more than that, we can subcluster them using our bank controllers. But this is another illustration of each bank having more and more genset. So that's mostly from my end. Before we move to another example, I would like to show you a simple illustration of something like this. Say, for example, you have, okay, maybe this one is better. So when I have multiple genset and multiple utility and in between a bus tie, let me just switch on my video. You will be able to see an illustration. So there is a multi-kit which which I have prepared for you to kind of illustrate the system operation. So just hold on. Just need to set up. So as you can see here, um, on the top half, I have one utility incoming here, and I have two generators, generator 1 and generator 2. So this is one half, one cluster. Similarly, on the bottom half, I have another utility here, and I have two generators taking care of the load on this half. So for example, here I have my utility is healthy and it is currently feeding the load. So let me reduce the load here. Okay, so currently it is feeding around 127 kilowatt. So if I would, and now it is currently operating even in manual mode. So if I want to manually operate the whole site and I want to trip the grid and see how do I start and stop everything. So if I fail the grid here, the MCB will open up on my utility end. That means there is no load, nothing, and I have to go and press my MCB manually because it is in manual mode, but my gensets won't start here because there is no auto mode operation given to the controllers. So if I have to manually go and start my genset, which is pre-starting, similarly I will start my second genset, which is also starting. Both of them will start and they will wait for my command to close the generator circuit breaker 1, generator circuit breaker 2. So once the system is stable and there is no more timers here, so no timers, so I will close my generator breaker. One is closed. Similarly, my second genset is running, it's almost there, so I can go and give the command to close the breaker, which will start synchronizing with the first one. Yeah, so it is trying to synchronize now. You can see the synchroscope is coming up, and once voltage and phases are matching, so now both of them are running on um, like paralleling mode, but there is no active kilowatt, so they are not fighting each other. Once I see everything is operational, I just go and close the MGCB, and now the gensets will start load sharing between them, so they can keep taking more load, and it will perform standard load sharing and var sharing. Similarly, on the bottom half again, if I would fail the utility, open up the MCB, and I would manually go and start the generators. So the gensets would start up. It will go to the nominal RPM. Once they are ready, I can synchronize, but they are independently working. So this is my top half, this is my second half. Okay, no timers, so I can close the second breaker and I can close this one as well. So now it is trying to synchronize. So there is sync timeout running in. Once they have synchronized, they are ready, and I can close the MGCB. So it is feeding the load as well. So they are stable. There is some load sharing happening between them. Once I start loading, they balance out. Now, say for example, if my genset number 4 broke down, or there is some maintenance going on, so I would stop, say, the 4 genset. Now my one genset is too much overloaded and I don't want to it to suffer alone. So I can combine the bus type breaker. So that means I'm clustering this two genset with my second powerhouse by combining this bus type. Now before I do that, because this is a live bus from first half and the second half, so these two generators are feeding the left bank and the single genset is feeding the right bank. So once I press the close BTB, it will perform synchronization again between them. So it is synchronized and the bus tie breakers are closed. Now you will see the load is changing between them. Now it independently, immediately the load on the third genset fell down and they are equally sharing the load between them. That's manual operation. But if I switch the entire operation to suppose auto mode, let's go to auto and let's go to auto here as well. And even this guy at auto. So now everything is in auto mode, but you see the genset tripped because this controller was not in auto mode. And I'll set it up auto here as well. Now all the systems are starting again. They will try to synchronize and take care of the load. So the first genset started because there is a grid failure. So valid grid failure happens. Second genset is also starting. It is feeding up the load. Second one would start and synchronize with the first one. So now everything will happen automatically. Once I do not have to touch, I do not have to control the breakers. So it is feeding up the load now. So they are load sharing between them. You'll see the kilowatt is going down. So, but my load is unbalanced. So there is a trip signal. I just go and press a fault reset, reduce my load on the simulator, and you will see the system will restart again, and it will synchronize again to the system and take care of the load. And if you want to see the synchroscope or anything, you can just go down. You can see the parameters. So it's already synchronized. So they're feeding up the load here. So basically I have top 3 gensets running. The fourth one is on out of the bus. And if I would return the grid back to normal, so if I bring back the grid, so mains return, so it will check if the grid is healthy and it is restored. It will automatically synchronize here. So you can see the grid is trying to synchronize. So grid synchronized, and gradually the load is getting transferred. So there's a breaker overlap we are performing. And once all the load is transferred back to the grid, the MGCB opened up, and now the gensets are going back to standby mode. So that's how you can see in manual and in auto mode the system operates. So that's all from my end.